Toby Parkin and David Rooney will be coming to talk in about 20 minutes. We're both curators at the Science Museum. I'm a curator of interactive galleries and David is a curator of maths. We have 2 new galleries that are opening over the next few months. I'm going to be talking to you about my gallery, which is called Wonder Lab, the Stator Gallery, that will be opening in October. It is primarily a science gallery, but it is interactive, so I'm going to just share with you a little bit about the process we go through. It does have a zone within it that is all about maths, so I'll share with you as well what maths exhibits we'll be displaying when it opens. So I just want to just start off with a tiny bit of history. We've been making interactive galleries initially for children at the Science Museum for a very long time. 1931 was when this photo was taken. And I think they're time measurement devices, those they're looking at. Very staged photo there. And initially, the concept of interactive galleries was that we wanted to fire the imagination by letting children control the miracles of science and make them feel that science is a wonderful thing. So in many ways, that hasn't changed. We've slightly shortened that message slightly, but that's still what we want to do. So I've been working on this gallery for about 2 years. We started off by being inspired by 2 events that were in the Romantic era of science. One of them was the Faraday Lectures at the Royal Institution, and the other event was the Great Exhibition, obviously in Hyde Park in 1851. And this was a time when the public were fascinated with science. The science that was shown and technology that was shown at both of these events was really simple in some ways, but it was really clearly explained. And so we're not trying to recreate these events at all, but we do want to recreate that public fascination when science and maths are really clearly shown and simply explained. So there are 3 kind of main take-home messages for my gallery. We have over 50 hands-on and sensory experiences. It's all about the wonder and the beauty of science, and the gallery as a whole helps you to think like a scientist. And that think like a scientist is just something I want to just pause on for a second. Interactive galleries play far better to skills rather than to factual knowledge that people take away. So we are hoping that people will display the skills of thinking like a scientist by using the interactives that we'll be presenting them with. What we mean by think like a scientist is we've split this into 3 words. These aren't all of the skills of a scientist, obviously, and these skills are by no means unique to science or to maths. But we want people to be curious about the world around them, to ask questions. We want them to pay close attention. We want them to be observational, to take in data so that they can then ask questions about that data. And we want them to be creative as well. So we believe scientists and mathematicians are inherently creative people. They come up with new ideas and they creatively problem solve. These are skills that everyone has. And so that's why we're playing this gallery to skills. Just to show you some visuals of what it will look like. It's still being built at the moment, so I don't have any finished visuals. This is a view from when you first walked into the gallery. It's about 20,000 square foot, so it's quite large, and it has a whole mixture of different types of experiences that I'll be talking about later. In the centre, you can see that there's a giant model of the solar system with a star canopy hanging above it. That's our central exhibit. It's on a rotating 7-metre turntable as well, so our visitors can stand with the Earth and the Moon, which will also be rotating, and they can move around the Sun and they can see all of our star canopy. We've positioned the stars with help from the European Space Agency, so they are in their exact positions for the closest 500 stars to the Sun. So you can see how we form constellations and things like that. This is the math zone, which is closest. We've got about 10 exhibits in the math zone, and I'll be talking to you about each one in a moment. This is the map of the gallery. This is generally kind of what it looks like. It's split into 7 zones. The first zone that you come into is about light, and then at the top we have forces, electricity, and maths is at the top right. Space is in the centre, and then we have sound and matter as well. And we have a show space on the right-hand side, which looks a bit like this. So it's based on the Royal Institution's Faraday Lecture Theatre. So the first experience that you come to is a colour room. So it's monochromatic light that's cycling from red to green to blue. We wanted to have this as the first experience, setting up as a slightly different gallery to the ones we've done in the past. Classic interactives are similar to the ones you saw in the children's gallery that I showed you earlier, where you hit a button and something happens. We call those closed interactives, and there's nothing wrong with closed interactives, but people tend not to stay at them very long. Children especially will run around a gallery hitting all the buttons and they won't necessarily hang on to see what's going to happen. So we do have closed interactives. People do like buttons and they do take something away from them. But we're setting this gallery up as slightly different. So this is an immersive sensory experience that you walk through as you come into the gallery. These are just reference images. That's Oliver Ellison. So this isn't literally what it will look like. And then as you come in, you're faced with the matter zone. So on the right-hand side, we have a chemistry bar, which we have a Dutch glassware maker who's made literally a ton of glassware to go into that. So that's the chemistry bar there. That's all of the glassware. We'll have bubbling science experiments. It's got glove boxes down here, so you can put your hands in and you can handle some slightly more dangerous materials that sometimes you're not allowed to use at school, so things like mercury. And on the other side of that bar, there will be explainers, so our staff who are in the gallery explaining scientific concepts. With things like liquid nitrogen, dry ice, they'll be showing these kinds of things to the public. I talked about our orrery, which is in the centre. It won't look exactly like this. People generally won't be literally on the planets. But it is on a big turntable and there are stars above it. And we can flick a button and the sun will become super bright. And you'll be able to see how we get eclipses and day and night on the Earth and seasons and things like that. We have an electrical demo area, which is this area on the left, with a hanging Tesla coil, and we'll be demonstrating Van de Graaff generators and big electrical items. There's a huge 3-ton tree that we're putting in front of the electrical demo area, which is studded with 1,000 magnets, and we'll be giving people metal washers, and they'll be creating their own magnetic branches from those. We have some slides in the gallery. These are our friction slides. They're 3 lanes. One of them's made of grass, artificial grass. The central one is fiberglass, and then on the left is a bowling alley. And this is a great example of giving young people especially a tool, and then they just think like a scientist, sort of without realising it. And then our job is to reflect that back to them and to realise they're thinking like a scientist. So what generally happens is children will try, when we've tested this, they'll try and find the fastest slide, so they'll think generally it's the bowling alley or the fiberglass one, and they'll go down it, they'll race against their friends, then they'll try and become a bit more aerodynamic, they'll take their shoes off. Without realising it, they're kind of doing a science investigation. They just need to realise they're doing that, so that's our job in interpretation with our explainers to reflect that back to them. We have quite a few artworks in the gallery. We're working with about 15 different artists. This is a prototype version of our concave mirror. It's made up of 200 smaller mirrors, and if you stand in the right point, you're reflected in all of them. And if you stand in the right point with a friend, you can see your friends reflected in all of them. We have a waves exhibit. This is replicating, or it's kind of a metaphor for a sound wave. It's connected by 2 motors, and it's a piece of elastic. You can control the speed of the motors, and you can change the phase of the wave, you can change the amplitude, you can change the frequency, and you hear the difference from the whizzing of the wave as you're moving all of those things. So this was made by an artist called Daniel Palacios, who's based in Berlin.
Is that a spinning, whirling?
Yeah, so this spins, yeah, so it's moving very, very fast. We have another immersive exhibit called Step Into the Light, which is inspired by, if you'll know, an artist called Anthony McCall. He does work of this nature. So it's a smoke haze-filled room with a projection of light that's slowly turning. You can literally step into the light, and we'll give people mirrors to reflect the light around. And it shows very simply that light travels in a straight line. I wanted to talk about maths, so I'll show you what maths exhibits we have. We did a lot of research initially into what our visitors think about maths. It threw up some things that I think probably are common, and nothing really new, but it was helpful for us to do that research. We found that our visitors, adults and children, are a bit scared of maths. Some of them love it, obviously. Many of them don't love it, so there's a slight issue there. And there's a performance anxiety with maths, which you're probably familiar with, and in school sometimes maths is taught to the test. We also did some research with teachers and parents and talked to them about what they wanted us to do in terms of our maths exhibits, and this is what they want our exhibits to do. They want them to be playful, they want experimentation with variables, they wanted logic and reasoning, they wanted discussion, analysis of data, connection to the wider world, concepts at a variety of levels, so low barrier entry but high ceiling for exploration, as someone said earlier, and explain a presence as role models and help with understanding. So there's nothing new there really. We sense that's what they'd say, and we've tried to respond to that with the exhibits that we've selected. Just a quick way on how we categorise our interactive exhibits. There are lots of ways to categorise interactive exhibits. The way that we commonly use is to split them into open and closed and passive and active, and try and balance out the types. So a closed interactive, as I said before, is where you hit a button and something happens. An open interactive is the opposite. This is a good example of it. This is an air vent. It's quite a common interactive that you'll see around the world. It's a jet of air flying up into the ceiling. The idea is you make your own flying machine and you set it off, and you see how long it will stay in the air for. So you're learning about lift and aerodynamics. That's open because there's no end to the content there. You could be perfecting your flying machine forever. There's an endless amount of variables. Open and closed, passive and active are to do with the physicality of exhibits. So one extreme passive is where it's purely observational and there's no physical interaction. And active is the opposite, is kind of what you see in a playground, is highly physical. So we try and balance these. If you have too much of one type, you skew your gallery in the wrong way. So if it's all active, it's a bit like a playground. If it's all passive, it's a bit boring. If it's all closed, people hit buttons and they run around. If it's all open, you lose the pace and the energy. So we literally plot it onto a graph. It's quite subjective, but all the 50 or however many there were when we did this originally, 60 exhibits in there. Ideally, we're trying to be in this quadrant up here, which is active and open. That's the kind of golden zone for us that we're trying to be in. So we will skew towards that quadrant. It's quite subjective, but it's just quite helpful in terms of balancing and curating a gallery like this. We have decided in terms of interpretation to use illustration. The reason for doing that is we can cut down on the amount of words that we use. People don't like to read in interactive galleries because of the energy levels, because sometimes you don't need to read in an interactive gallery. The exhibit should be delivering all the content on its own. So this diagram here, or this illustration here, stops us needing to say push the button, which is my pet hate in terms of interactive galleries and labelling. And we also can bring out some context here of everyday life. So these are the exhibits we have. Again, some of these probably won't be new to you. You'll be familiar with them. We haven't really tried to break the mould too much with these exhibits. So this is a laser cross-section exhibit. On the top left, we have a harmonograph called Pendulum Patterns. This is an exhibit that we did sort of come up with ourselves, and we worked with an exhibit maker. It's to do with parabolas. It's sending out a jet of laminar flow water, and you're trying to hit a target, and you set the angle and set the laminar flow water off, and you try and hit the target. And if you hit the target, all the lights go. So that's one that we came up with ourselves. Quite proud of that one. We have an exhibit called Sip or Spray, which is the prisoner's dilemma. Probably don't need to explain it, but yeah, you see what I mean. And then on the right-hand side, it's just a simple 3D shape builder out of 2D shapes. We have a tessellation wall at the top, so we've worked with an artist called Siobhan Liddell to design our shapes for us. And at the bottom we do have a puzzle area, and we have about 5 different puzzles in that area. We've worked with an artist to make all of our puzzles. So those are the 7 or 8 maths exhibits that I just wanted to share with you. I'm coming to the end now, so I hope that's been useful in terms of the process that we go through in terms of an interactive gallery. There's a lot more depth to it, and it's quite nuanced. People walk into interactive galleries and they think, oh, it's quite easy, you just pick all your favourite exhibits and put them in a room. Don't do that, that's a terrible idea. So you have to have some thinking that goes into it. We've also brought out a book. It's called This Book Thinks You're a Scientist. It's linked to the gallery, or all of the zones, or each of the chapters, so there is a maths chapter in the book. It's an experiment book where you can do experiments without needing much. So we've done lots of experiment books at the Science Museum where you need to get lots of equipment. This one you mainly use the book itself, so you probably just need some scissors and a pen, and then you do everything with the book. Yeah, so that is everything from me. I'm going to pass over to my colleague David Rooney now, who will be talking to you about our maths gallery.
Thanks, Toby. Can you hear me at the back? You might regret that. I'm David Rooney, and we're opening a gallery in December as well, which is a history gallery. And it's a really interesting question, I think. If you're going to make a gallery on the history of mathematics by displaying historical objects, what are the objects that represent mathematics? Here's the boilerplate. This is what we're opening in December. It's a fairly large gallery. If any of you know the old mathematics gallery at the Science Museum, it's in the same space that occupied. That gallery opened in 1975, and it was the Science Museum's representation of mathematics and mathematics history until we closed it a couple of years ago. The new gallery is designed by Zaha Hadid Architects, and it covers 400 years of the history of mathematical practice. telling inspirational stories through historical artifacts. So what are those artifacts? And the really interesting question, I thought, with the old gallery, with the 1975 gallery, I don't think that it was that it had dated and that it had started out well in 1975 and had dated badly. I think it had some flaws from the start. If you visited it, the objects which were chosen to represent mathematical practice through its whole glorious, broad, diverse and highly important history were showcases full of slide rules and showcases full of drawing instrument sets. Also tools that a very small number of mathematical practitioners might have used, or
I remember vividly.
or mathematical surface models, so shapes that mathematicians use to describe physically some of the equations that they work with. Now, as Toby outlined, for the vast majority of our audience, they're not mathematicians, but much more significantly, they dislike mathematics. It's not an antipathy. It's not that they're not sure what they feel. They actively dislike it. Our research showed this. I'll talk about that more in a moment. So there's a real challenge in a history gallery to explore what mathematics has done in the world through objects. And I think the old gallery didn't do it. And so the real challenge for us was what is the set of objects which is a material culture of mathematical history? What are the objects that represent math? Now, so we started this maths project 2 or 3 years ago, and what Toby's outlined is the hands-on interactive gallery which opens, which is a terrific way of talking about mathematical principles, mathematical ideas, mathematical approaches. And so that kind of enabled this history gallery not to try to do that. So what I think is rather important to say is that the History of Maths gallery is not teaching mathematics, it's not teaching mathematical principles, nor is it a history of mathematical ideas. It's a set of inspiring, we hope, stories about people from the past who have used mathematics using a very broad definition of that in the last 400 years to change the world. As you can see from this render, my gallery too is a building site, so I'm afraid I can't show you that either. And this picture really does not do justice to what the Zaha Hadid gallery looks like. It's the most extraordinary experience working with her practice. As you can see there, there's an aeroplane at the centre of the gallery. It's a real aeroplane from 1929. More on that in a moment. But that's to give you an idea of what might a mathematical object be. It could be anything. Because if you take our fundamental conceit for this gallery, that mathematical practice is underpinned and has been driven by some of our most fundamental human concerns through history, then that raises a really interesting point. What are the sections of this gallery? What are the zones? How do we divide up this story of 400 years of mathematical practice? Now, conventionally, we might choose categories internal to mathematics. Probability, statistics, logic, symmetry, whatever. But I think it's so much more significant than that. And we've got such an opportunity here to talk to people who aren't internal to mathematics, but might very well be inspired by it. And we can perhaps try to change that public relationship with mathematics as a concept. So instead of dividing the gallery up by mathematical concepts, what about dividing the gallery up by some of our most fundamental human concerns through history? That's the point. So you don't need to know how maths works to understand that we've always cared about war and peace, trade, travel, money, life, death. These are fundamental. I mean, at least for 400 years, but probably forever we've cared about these things. So let those be, we thought, our 6 zones in this gallery. And for each of those zones, let's pick just 3 or 4 stories where we have an object in our historical collections related to that story which says something about mathematical practice and trade or travel or war or peace or money. And let's just tell some stories about that through our objects. So you can see the sorts of stories that we're going to be talking about. And some of them look mathsy, recognising patterns, solving equations. Some of them perhaps look a bit less like mathematics, like mortality or navigation, architecture. It depends how much you're into the stories. But these are the 21 stories that we're going to be telling in our new gallery that opens in December. And each of those stories is told through just one main object and then maybe 3 or 4 subsidiary objects. Because the worst thing that we could have done in this gallery, where of a subject people might expect to be overwhelming, is to give them an overwhelming physical experience of hundreds of objects that they feel they have to get through before they're allowed out. And I should point out that the average duration of a visit to a free permanent gallery at the Science Museum is 12 minutes. Sorry, for a successful free permanent gallery, 12 minutes. It's very much lower for the unsuccessful ones. Now and we might want that to be different, but that is the truth of the matter. So what maths could we teach in 12 minutes? And it seems to us that instead of trying to teach, a very, very simple piece of maths in those 12 minutes, why don't we just not try and teach maths at all and just tell some inspiring stories? So some of the objects that represent those stories. So in the centre there is the aeroplane that hangs in our gallery. It's in there now. It's the first object that went in. It's from 1929. It's the most gorgeous biplane. It's a unique object by Handley Page, the Guggenheim, 1929. It was made as an experimental aeroplane for a competition sponsored by the American industrialist and philanthropist Daniel Guggenheim, who wanted to kickstart a civil aviation industry in the 1920s. And for a civil aviation industry, it really needs one thing only, and that is trust. Trust in the potential passengers that the aircraft is safe, that flying will not kill you. And the first civil airlines, which started around 1919, 1920, really had to struggle to fill aircraft. When aircraft only had 6 seats for passengers, they'd struggle to fill 6 seats. So there's a real problem here, because the aircraft was a military weapon and safety wasn't the prime concern in the First World War. So let's hang an aeroplane there. It's got some interesting aerodynamic stories. We can tell the story that civil aviation was a huge employer of highly trained mathematicians in the First World War and after. We can expand that out and say, who were those mathematicians? Where were they studying? They were studying at places like Cambridge University, Imperial College London. We can look a little bit further. We can find out that many of them were women who worked in the First World War because, the men were out fighting. And then after the First World War ended, for just a few years, many of those women stayed in the civil aviation industry before men came back and crowded them out. And so we can tell some stories about some mathematicians. They're not the great men of mathematics. They didn't advance great theorems, but they created a multi-billion-dollar aviation industry that we all get. We all understand that their work is significant. You might be interested in architecture or skyscrapers. So we've got, an architect's model of the NatWest Tower. How do buildings stay up? Well, a really interesting history there of structural engineering and civil engineering. You might be interested in the economy. You might wonder why you've not had a pay rise for a few years. You might wonder what's been going on since 2008. Well, we've got a model from 1949 made at the London School of Economics that attempted to model how the economy works using the flow of water. There's a hydraulic computer made by the economist Bill Phillips, pictured there on the right, which used fairly deterministic equations to model the economy. You turn up the interest rate and you turn down money supply and, what happens? Well, that's really very interesting. Now, in the old gallery, it was displayed. Sorry, I'm ranting slightly. It was displayed as an amusing byway in the history of computing. Isn't it funny that in 1949 they made a hydraulic computer rather than a digital one? Which misses the point of that object entirely. It's highly significant that 2 generations of Treasury economists trained at the LSE were trained using ideas expressed by that machine. So for 10 or 15 years, economists who went on to work in places like the Treasury and big business were trained using that machine in their lectures, which expressed a certain mathematical view of how the economy works, which you might argue, once out in the wild, once the limits of the models have been perhaps forgotten by some of the practitioners in business or whatever, or in government, the decisions being made 20, 30 years later have been affected by a mathematical worldview expressed by that machine. That machine is of incalculable significance culturally. And it's a story of the history of mathematics. And it's a story that we care about because that machine is led to the crash. Discuss. But you can have a really serious conversation about the significance of mathematical modelling, if you wish, and about limits of models, and about who operates models written by other people, which I think is of profound social significance.
Was it a Keynesian hydraulic model or a neoliberal?
Well, how long have we got? Right, okay, right, stop the clock. That's a really interesting question. With the question there, was it Keynesian or was it classical or neoliberal, did you say? Very interestingly, because it's hydraulic, the plumbing was able to be broadly speaking, Keynesian, because it was in the 40s, 50s, but it could be re-plumbed to operate neoclassical, not quite neoliberal at that point, but it was just starting to come in, but you could run neoclassical, no problem at all. Moreover, it was UK only, but if you plumbed two together, you could run exports and imports, and you could run deficits. Seriously, this...
If it's any use, it was being run in Cambridge when I was there, and Stones always came wearing Wellingtons.
Absolutely.
The clock has not stopped.
God damn it. So you can start to see these are just a few of the objects, some of which are, small, beautiful calculating machines from the 17th century. Some of them are the LSE model. Some of them are equation-solving machines. That's a differential analyzer from Manchester University, which in the old gallery, it's a machine for solving equations. And in the gallery, the labels talk about torque amplifiers and partial differential equations and all these sorts of things. Well, that's fine if you already care about the machine enough to know what it did. What it didn't say on the label was that actual machine was used for just a few weeks in the Second World War to calculate the uranium enrichment equations which led to the first viable atomic bomb which was dropped on Hiroshima. So on the road to Hiroshima, that machine was used to calculate some crucial Manhattan Project mathematics. So this is not to be any kind of judgment, but it's to say to our visitors who react well to this that mathematical practice, scientific practice, is part of society, is part of culture, and it's practiced by people. This is a story and a gallery about people. I mean, we're telling it through objects, but those objects are made by people, paid for by people, sponsored by, modified, maintained, shut down by people for social, cultural reasons. And these stories our visitors find are inspiring. So we hope that once they start to think that mathematics is part of my world, that maybe they'll have different conversations with their kids when they're talking about which subjects they might study moving on, or the kids might think differently about the subjects they take because they can see the broadest range of industries or subjects that a maths education might lead to. Let's talk about the architecture of the space. We had the competition a couple of years ago, an international competition, as all of our galleries, to find an architect, to find a designer. And Zaha Hadid pitched this. And what she did, she trained, as many of you will know, first as a mathematician herself. And all of her architecture was, and since she died earlier this year, the architecture of her practice remains driven by mathematics. It's new geometries driven algorithmically. She employs mathematicians. She has a department of coding which generate the geometries of her architecture. So when she hung up in her model the aeroplane that I showed you earlier and said, imagine that the gallery is a wind tunnel, let's mathematically model the airflow using the Navier-Stokes equations around that aeroplane, and then let's make that physical. Now, in the first slide, I'll not rush back to it, in the first slide you may have seen the aeroplane, and surrounding it was a curved purple-ish structure, which is made from fabric. It's being fabricated in a facility outside Bristol as we speak, which is the mathematical solution of airflow around our aeroplane. And then in plan view here, you can see that the showcases are laid out along mathematical lines of airflow with bits of turbulence, bits of laminar flow. So whilst it doesn't matter whether you get this, the gallery itself is a mathematical artifact in its own right. We hope people will get it because we've made a rather delightful, I hope, film underneath the aeroplane as you sit comfortably on a bench to explain just how the gallery, the aeroplane, the structures around you are themselves mathematical. I'll skip over this. I mean, the audience, Toby talked about, the audience research that we do. This gallery is not largely aimed at formal school groups, although they will be using it. It's aimed largely at independent adults and families. It says there for children aged 8+, actually the reading age is about 12+. Most family groups come intergenerational with kids of varying ages, so we've gone for the reading age of 12, and then the rest of the family group interpret for the younger kids. That's how it works in a family visit. I mean, it's kind of fairly obvious to us. Our research did show that there were significant barriers to engagement with mathematics for many people, but if we could link the mathematical ideas to the people, to the impact that those ideas had on the world at large, to give that context which we've heard about already today, then people can feel a connection. We use a sparing amount of digital media to tell stories beyond the fixed text labels which will tell the stories for all of these exhibits. Some of those are about how it works. Now, you know, if you've got an astrolabe or an Enigma machine, you'll want to get your hands on it. Well, we have historic ones, we put them in a glass box, and we can't allow you to send your Enigma message on the historic one, so we've made a digital simulation of that. Similarly, how an astrolabe works, we're making one of that London School of Economics hydraulic computer, and so on. You want to find out more about the maths, the history? Well, we've made touch screens for 9 of the stories. And crucially, they also include a series of film interviews that we've made with practitioners in industries today, represented by historical objects in front of you. So you might see a Victorian tide predicting machine from Lord Kelvin about predicting tides. Well, we've interviewed people at the National Oceanographic Centre in Liverpool and Southampton. So who are the oceanographers, the tide and surge predictors today? And we've chosen to interview people who are largely early-ish career rather than late career. And we've chosen a broad range of people, a broad demographic, to show that these are the practitioners of mathematics, whatever you might think, that this may be a male subject, an old male subject, a white male subject. So this is highly important for us to show that mathematics is highly broad. If Zaha Hadid, an Iraqi woman, can become one of the most noted architects in the world, that's a strong story. It's a strong math story as well as an architecture story. I reckon I've got about 2 minutes left, so I'm going to talk about just a couple of the objects, one of which is about gambling. Now, I misspent a childhood. Not a childhood, I mean, what am I saying? Teenage, going to dog tracks. We have the... and I was terrified of the turf accountants, trackside. I didn't understand how they fixed their odds, and however the totalisator machine, I could understand that there was some system, a machine, which would set the odds. I didn't really understand pari-mutuel betting then, and still to this day don't fully either. I'm not a mathematician myself. But we have the totalisator machine from Wembley Stadium, and this is the odds machine which we'll be displaying. And you know, there's a reason why it's triangular, because the function that it was solving was a trigonometrical function, and it actually used motors to motor the length of the opposite side of each of those triangles in and out as punters placed bets at the windows. It was solving it physically. There's a remarkable pattern drawing of that, which we'll be animating. Who are the mathematicians? Well, we're going to be talking about all kinds of mathematicians, people whose names you may not have heard of, the aerodynamicists at Handley Page, for instance, but also people you have heard of but may not have known were mathematicians. It's widely known in maths communities, of course, that Florence Nightingale was a statistician, but it seems not widely known in the wider public. And so to say that somebody who had... To try to counteract the gendered story of Florence Nightingale, of the lady with the lamp, the nursing, the caring profession, to revise that slightly seems rather worthwhile. Finally, I just slipped in there that I'm not a mathematician. I'd studied very, very many years ago physics So I kind of, I can have conversations with scientists, engineers and mathematicians, but I think actually not being a mathematician may just have helped for this particular gallery. Having said that, of course it's vital that I was surrounded by mathematicians who could check what I'm saying, but could also share with me the culture of mathematics that I'm trying to represent. So we had an advisory panel, as we do with all of our galleries, and it's fairly well balanced between mathematicians in academia and industry, historians of mathematics, and maths education specialists. And Margaret Brown has been on that panel right from the start, and we've hugely appreciated her contribution and those of the others. We had a mathematician in residence, Thomas Woolley, 1 day a week. I'm sure he tore his hair out a great deal, but anyway, there's plenty left. We got a book out as well, just in time for Christmas, ladies and gentlemen. Mostly written by me, you can ignore those bits, but the essays at the end by the people that you see listed there give us some new insights into mathematics, its history, its practice and its future. And just to point out, as I say, Zaha Hadid and Patrick Schumacher, her business partner, both trained in mathematics. David and Claudia Harding, the funders of this £5 million gallery, were mathematicians, and their company, Winton, has used mathematics to make colossal amounts of money, which we've been delighted to help spend. And the relationship with the funder has been absolutely terrific. This is really important, this project, to us. We hope to try to reshape the public's relationship with mathematics, not to teach it but to inspire. So it's probably time that I shut up, so I will. Thank you very much.